Okay, welcome back and greetings, my fellow engineers. So today we're going to talk about the ARM pipeline architecture. And one important caveat is that if you find that you're still confused or not sure about the single cycle architecture, I would strongly recommend that you stop this video and go back and really make sure that you've covered that first. It's really going to, we rely so much on that understanding when we take it a step further, when we look at the pipeline implementation, that you're going to really want to make sure you have a solid foundation on that prior to going into this topic. Okay? So, with that being said, let's just jump in and press ahead here, and let's look at what is the ARM pipeline, or what is a pipeline implementation. So we're talking about a way in terms of we're building a processor, we're implementing a processor, and if we're looking at how a CPU is designed in a single cycle implementation, which is an oversimplified view, but a good kind of starting point to be getting into these concepts, is if we look at the single cycle implementation that we've discussed previously, we have this idea where we've got this one big long clock cycle in which the entire instruction starts and finishes within one single clock cycle or one clock period. Okay, so we can see here by looking at this this image that we've got the state element, say, starting at the rising edge, and we have some combination of logic running through the falling edge of the clock cycle, and this all has to finish by the time we get to the next rising edge. Okay, so we have a bit of a restriction when we look at the single cycle implementation. The single cycle implementation has one big long clock cycle that needs to be as long as the longest instruction that we have. Okay, so the longest instruction, the instruction that's going to take the most amount of time, our clock period must be at least as long as that longest instruction. Okay, so that's an important thing to know, and we'll see a little bit later on that longest instruction is actually the load instruction. Okay, it's actually the load instruction, but we'll discuss a little bit why in a little bit. Okay, so let's look at a very popular analogy for how the single cycle architecture in a CPU is designed. Okay. And it's an oversimplified design. It's really used, as I said, as from an educational standpoint before we look at a more realistic implementation where we have a lot happening in parallel. So let's look at the single cycle, and let's do this as an analogy using laundry. This is a famous analogy that's been used a lot to describe these concepts. Now, if you let your laundry pile up and you got an awful lot of laundry to do, you probably don't do what is described on this slide. Okay, and in this slide what we're seeing an example in which, imagine we're taking the laundry and we're breaking it out into 4 steps. Then we have a step for doing the wash, then drying, then folding, and then asking someone to put away your clothes, right? And so this example is asking, step 4 is saying ask your roommate to put it away, so that in theory you're available to be doing some of the other steps in terms of transitioning things. I don't know about you, but when I was in college, I never had a roommate that would be willing to do my laundry. But for the sake of this example, we'll kind of press ahead with it. So there's an obvious inefficiency in this design that we're seeing below. Let's imagine each step here takes 30 minutes. So that we have 30 minutes to do the wash, 30 minutes to dry, 30 minutes to fold, and 30 minutes to put the clothes away. Okay? And the example below is we're doing one complete load at a time. We're washing, we're drying, we're folding, we're putting the clothes away, and it's not until that entire load has been done that we are now going back and saying, okay, now let's do another load of laundry. Okay? This is clearly not how people do a lot of laundry, right? For the very obvious point that you are having resources stand idle while you have this period of time where you have, say, a wash. Like if you've got something in the dryer, you could have something else in the wash, obviously. So we can use this aspect of basically being able to use parallelism, right, by the fact that we can use have multiple things happening or multiple loads of laundry happening simultaneously, we're going to promote greater throughput. We're going to promote a more amount of work being done in a given period of time. Okay, so that is the idea of a pipeline. Okay, just like the laundry. Well, the goal here is we don't want to have our resources being sitting there idle. Okay, and the moment, like just like the analogy of the laundry, is the moment something is done in the wash, right, and you can move it over to the dryer. Now that washer's free to start putting the next load in. Okay, and this is just like how we can have when some sort of hardware resources become available, we could say, okay, use that to start processing the next instruction. Okay, start processing the next instruction. Okay, that is the idea. That's the idea. If you understand that simple analogy, you've come a long way in understanding how pipelines work. Okay, now we got to take that kind of high level understanding and go into how we actually implement it. Okay, well, let's notice something. First of all, let's notice how in this example here, in this analogy, there's a few key pieces of information to kind of make note of. Okay, one is notice that we broke out the step or broke out the process of doing laundry. We broke it out into 4 steps. Okay, we broke it out into 4 stages. Okay, we're gonna do something similar when we go and look at how we actually process an instruction in our processor. Okay, instead of 4 steps, we're gonna actually break it out into 5 steps. Okay, we're gonna have 5 steps that we use and how we break up the steps involved in executing or processing an instruction in a computer CPU using a pipeline architecture. Okay. Now, that's one thing to note, right? Before I move on and kind of look at those steps in more detail, I also want to note that we have a clear limitation with even our pipeline example, and that the most efficient way of breaking up the instruction into different pieces, or breaking up the process into multiple pieces, is that you have the ideal situation is that each stage, right, each stage in the process or each step in the process is a fixed same or identical amount of time, right? So imagine the ideal situation of doing laundry, for instance, is that your washer and dryer take the exact same amount of time. Same with folding and putting it away, so that nothing is ever idle. Okay, realistically, that is very hard or does not happen. Okay, so how fast you can process or move things along is limited by the speed of the slowest stage or the slowest step. Okay, so the ideal situation here is that we have these different stages, these 5 stages being of the same duration. We're going to look at that. We're going to have some assumptions that we use or some in this, and one thing we'll see is that that's not exactly the case. Okay. All right, but before we do that, let's look at each stage in isolation. Okay, so we've got these 5 stages: instruction fetch, instruction decode, execute, memory, and the write back stage. Okay, sometimes they are shortened to just have a kind of small number of letters that represent each one. IF for instruction fetch, ID for instruction decode, EX for execute, MEM for memory, and WB for write back. Okay, just to note, sometimes we're going to have some notation where we see those later on. Okay, let's not get hung up on the specifics of each stage. I think it's easier to see a visualization of them instead of just reading off some of the definitions of what's going on. All right, so let's look at some pictures. If we look at the data path for the instruction fetch stage, we're basically doing the following, right? We're reading instruction memory, okay, so that we get an address going in instruction memory, and out comes the machine language instruction out of instruction memory. And we're also adding 4 to the program counter. Doesn't mean that we are writing it back to the program counter, okay, immediately, right? That's going to happen at the next rising edge of the clock cycle, okay? So we have this happening in the instruction fetch stage. Okay. And if we look at all 5 stages, and I'm not skipping over the other 4. I'm going to show you them in kind of individually. Okay. We can kind of draw these dotted lines here of looking at our, in this case, it's very similar to what we saw, a little oversimplified, of our single cycle implementation, and look at what's going on in each one of those stages. Okay. And what we have here, right, is the second stage, the instruction decode stage. The big thing happening in that stage is we are reading the registers, okay? And we could read 2 registers at a time, right? We've seen that before. It's not different than anything else we've already talked about, okay? But we could read 2 registers simultaneously, and we are going to read them in the instruction decode stage, okay? Stage 3. Stage 3 is our execute stage. The big thing happening here has to do with the ALU, right? Whatever the ALU needs to do, depending on the instruction. Does it need to add? Does it need to subtract? Right? Whatever the ALU needs to do based on that instruction, that's going to happen in the execute stage. Okay. Hence the name. That's, in some ways, that's doing kind of the heart of what the instruction needs to do, right? Like if it's an add instruction, it's going to add there. If it's a subtract instruction, it's going to subtract there, right? So that's hence how it gets the name. Okay. And similar to what we've seen the ALU use for our data transfer instructions, our stores, our loads, okay, they're going to do the address calculation. Base address plus the offset, okay? Just like before, there's really no difference. Stage 4, memory access, okay? Do we need to read from memory, right, in the case of a load instruction? Or do we need to, do we need, if we, from a load instruction, yes, we're going to read from memory, or do we need to write to memory like a store instruction, okay? That's happening in stage 4, okay? And stage 5 is a little bit funny, because that one actually wraps back around and writes to the register, okay? So the last stage is actually writing to the register. So is an R-type instruction, right? It's writing to the register, okay, the destination register. Okay, if it's a load instruction, same thing. It's writing to that register that needs to get that value that was at that memory address, okay? So those are the stages that are involved, and I think it's probably worth looking at a bit of a visual of the write back in particular of what's going on there, okay? We see here in red, because it's a little bit, it's the one that you can't kind of evenly slice the diagram and clearly see what's in there. It kind of wraps around and looks as if it's part of a previous stage. But keep in mind, right, writing to a register does not happen in stage 2, does not happen in the instruction decode stage. It happens in stage 5, the write back stage. Okay. All right. So those are the 5 stages. Let's go a little bit further with this. Let's note a couple things, right? And I'm going to just kind of update this diagram a little bit just to make it a little bit more clear of what's going on. Is we're here, what we're referring to is, oops, this is our branch, right? And this is our store, and this is our load, okay? Is I want you to keep in mind, right, just like what we're seeing in this diagram, is not every instruction takes all 5 stages, okay? And let me be very clear on this because it's going to be very easy to misinterpret what I'm saying, okay? All instructions, okay, will take all 5 stages to execute, but they're not necessarily doing work in those stages, okay? Let's go back to the laundry analogy for a moment to understand this. Let's imagine that you had a load of laundry and for whatever reason you didn't need to fold the clothes. You were going to just throw them in a clean pile or something. Okay? Well, even if you do that, right, you don't necessarily save any time because you've got other things in the other stages. You can't really necessarily do any extra work, right? Just because you took one thing that was running, one load of laundry or one instruction that's in your processor, and all of a sudden said, I don't need that stage anymore, right? They can't really do anything speed up because there's other things that are happening that are using other resources simultaneously, okay? So, give you an example, right? It is worth pointing out, though, that they don't necessarily all have to do, sometimes they're in a stage of the pipeline and they're just not doing anything except just being there, okay? So you think of an R-type instruction, right? Think of an add instruction. It doesn't use memory, right? doesn't write to memory, doesn't read from memory. Okay, so it's not going to use the memory stage. Okay. Store instruction does not write back to a register, does not use the write back stage. Okay. So, the loads are kind of unique in the fact that a load instruction is using all 5 stages. Okay, it's reading from memory and writing back to a register, right? It's using all 5. Okay. All right, so that's the thing that's worth mentioning, worth pointing out. Okay, and let's take a look. Let's kind of bring this back together and think of how does this compare to our single cycle. All right, if we kind of remember, the single cycle takes one long clock cycle to execute, right? So a single cycle implementation, and by the way, this looks a little different on the right hand side, but what we're seeing here with these instructions is these are all loads. Okay. The example actually comes from a different assembly language, but it's the same idea, right? A lot of times that we're looking at different architectures, and there's some commonalities between different ways in which they're all having the kind of same fundamental concepts. All right. So let's look at the single cycle. Let's look at this in terms of performance, right? Let's actually look at some numbers and say, well, how does this relate to what we're getting at, right? How does this relate to overall efficiency or a way that we can measure what kind of speed up we're going to get, okay? So if we look at the single cycle, we're going to have a couple assumptions here, right? Because we're going to have to assume some numbers that seem reasonable in terms of how long different stages would take, okay? And if we looked at the single cycle, if we assume that the instruction fetch, execute, and mem stage, let's assume that those 3 all took 200 picoseconds each. Okay, so let's assume that the IF stage, okay, the execute stage, and the mem stage, let's assume that each one of those took, not 200 picoseconds. Okay, and let's assume that the decode and the write back took 100 picoseconds. Okay, well, it's pretty straightforward to say how long would the clock cycle need to be. Well, the clock cycle needs to be at least that long, right? Because the entire instruction for the single cycle implementation must finish within that duration, right? It can't be any shorter than that, than summing up all of those. So if we did that, we obviously see that if we started at time 0 here, that it would take, we need a minimum of 800 picoseconds, okay? Right, or 0.8 nanoseconds. Okay? So that's our clock period, right? That's how fast our clock is going to be able to run. Okay, that's the length of the clock period for if we were looking at a single cycle implementation based on those assumptions for how long each stage would require. Okay. All right. So it's really fast, right? So it's under a billionth of a second. So there's not much different on this slide. So let's just kind of keep moving on here. If we look at actually how we measure this, a common way of measuring performance, okay, is this idea of throughput. Okay, of throughput. Throughput is an indication of we're saying, well, how much work is accomplished in a given period of time. Okay, how much work is accomplished in a given period of time. So the units that we're interested in that case is instructions per second. Okay, instructions per second. So if we look at this and we say, well, okay, we know the clock period, and since we know how long that the clock cycle is 0.8 nanoseconds, right? Well, we can pretty easily figure out then, since every clock cycle is running one instruction, we could look at that and we could say that this is going to be 1.25 billion instructions per second. Okay, sometimes that's written as GIPS, right? When we have G for giga, right? Okay, that's how fast. That's the amount of throughput, right? That's how many instructions per second we can run based on these kind of hypothetical numbers and based on these assumptions of our underlying processor. Okay. Now the thing is, let's take this back to where we're looking at the example with the pipeline and say, can we do better? Can we do better than this? Right? Well, and of course we can, right? We already saw that looking at the laundry analogy by doing things in parallel. All right? By doing this in parallel, of course we can do better. We can have better throughput. Okay? So if we look at this, right, if we look at the pipeline implementation, and now we're doing things at the same time, we're not allowing hardware resources to go idle. We're trying to have everything that is being used as much as possible. Okay? And I want to point out a couple things. For one, we can see that there is a little bit of open space going on with the registers. Okay? And what that is that open space is, there's one kind of thing to kind of point out here, is that we are using the register file is being used in actually two stages when you think about it, right? The instruction decode stage is reading to registers, okay? And the instruction write back stage is writing to a register. Okay, that hardware resource is being used at this by two different stages in any given clock cycle. Okay. However, this is how that is designed to work, right? We read from the registers in the second half of the clock cycle. So notice that the read is occurring, okay, in that 100 picosecond window in the second half of the clock cycle. That's basically happening in the falling edge, right? We've got the falling edge of the clock is going to trigger the read. Okay, so at that falling edge. Okay. The write happens before that. All right. Notice the write is going to happen, is going to be triggered at the rising edge. Okay. So the write is going to happen at the rising edge. So it happens first. Okay. So in any given clock cycle, right, at any given clock cycle, the write operation happens first, followed by the read. Okay. Registers can work really, really fast. They don't need the entire clock cycle to perform those operations. Okay, they can do it really quick. They don't need all that time. Okay, so that's an important caveat to note. And the architecture is designed to take all that into account. Okay, all right. Now, when we look at this, let's come back and say, well, what do we mean by looking at these in terms of performance? We want to look at we already looked at the single cycle. We looked at a measure of throughput. Let's do the same thing with the pipeline and say, hey, well, what's the throughput of this given these assumptions, given these hypothetical numbers, okay? We got the same hypothetical numbers as before, where we have the stage 1, the instruction fetch, stage 3, the execute, right? And we're going to assume that stage 4, the mem stage, are all 200 picoseconds, okay? And even though the instruction decode and write back only need 100 picoseconds each, okay, we still need to look at these as if they are 200 picoseconds. And the reason why has to do with something I mentioned a little bit earlier, okay? The reason why is, think about when you're doing laundry, the same thing I mentioned previously, is if you decided for one load of laundry that you didn't want to fold them, didn't want to fold the clothes, right? You don't necessarily have a speed up of the system, okay, if your washer and dryer and everything are already fully occupied, because you can't do anything else because the hardware resources are already being used to their maximum capacity. So you're going to be, even if you decide not to fold, it's basically having to sit idle during that extra time. It's the same idea with the pipeline, okay? Even though the decode and the write back can happen in half the time, right? They need to take that entire duration to operate, right? They need that entire clock cycle to operate. And another thing to note, right, is that unlike the single cycle where we have one long clock cycle, and we said we're going to have the single cycle had one long clock cycle of 800 picoseconds, okay? The pipeline is going to have a much faster clock cycle. In this case, our clock cycle for the pipeline is our 200 picoseconds, okay? Because we're going to time everything to happen, right? We're going to time everything to happen in each stage. The clock cycle's timing each stage, saying, okay, you completed one stage, go to the next stage. So we've got a faster clock cycle time, okay? All right, so if you understand that, right, we can look at how the throughput works, okay? And we have the same assumption, right? If we've got, when the pipeline's full, okay, this is ARM. When the pipeline's full, we are going to finish one instruction every clock cycle. Okay, so ignoring the first like 4 clock cycles where the pipeline's filling up, okay? When you have a whole bunch, when you're running billions and billions of instructions, right? When that pipeline's full, right? Every clock cycle, given some sort of strange things that, you know, some assumptions and stuff that we're going to ignore to make this a little bit more realistic down the road, every clock cycle we are going to finish one instruction. Okay, so this clock cycle time of 200 picoseconds, that's how long it's going to take us to complete one instruction. And once again, if we look at that in terms of, well, what does that mean in terms of throughput? Well, we've got the same thing where we're going to be able to do 5 billion instructions per second, okay, given these assumptions. Okay, that is 4 times faster than the 1.25 billion instructions per second that we saw for the single cycle implementation. Okay, this is why pipelining makes a lot of sense. Okay, that's why it makes a lot of sense to, right? Why not get that kind of speed up, right? Why, you know, you might as well not have hardware resources be idle. Make use of them. Make use of them at the best level of capability that you have. Okay. All right. So let's see here. Kind of just a quick thing to note, right? We are concerned with optimizing throughput. Okay? We're concerned with optimizing throughput. Latency is how long it takes to run one instruction. Okay? It actually is slower to run one instruction when you pipeline. Right? Think about it. We had an 800 picosecond time for the single cycle implementation based on those hypothetical numbers, and we had a 1 nanosecond time when we were doing our pipeline implementation. So it was actually a bit slower, okay, in terms of latency. Okay. However, those times are so incredibly fast. You're talking about a nanosecond, right? Or you're actually, in this case, you're talking about a difference of 0.2 nanoseconds, right? You're talking about a fifth of a billionth of a second, right? It's not something in terms of latency that you can really experience in terms of human terms, in terms of one instruction taking a bit longer to run, or any given instruction taking a bit longer to run. What we're concerned about is being able to maximize the amount of work in a given period of time, okay? So that within a given second, right, we can do the most work possible. And that's why, right, when we're talking about the design of these architectures, right, we're much more concerned, we're really concerned with throughput. We want to get the most work done in a given period of time. We are not concerned about latency. Okay. So that's an important thing to kind of just keep in mind. All right, so we'll do some practice. Let me stop there because this video is getting quite long, and we will follow up where we look at this and say, okay, let's actually look at the pipeline design. Let's look at it. Let's kind of pull some numbers out. Let's trace a couple things, and let's try to make sure that we have a good intuitive feel for what is going on. And once again, just make sure though this stuff is confusing when you're new at it, right? Sometimes it takes a little bit of time to click, but feel free, work through it, practice, and then feel free to reach out to us at any point if you got any questions, you want anything clarified. All right? Well, thanks for watching.